Hello, welcome to Everything Distributed. Today we are going to talk about the concept of partition, or some people call it sharding. And it's based on the material in chapter 5 in Martin's book. So what's partition? Actually, the idea is very simple. So suppose that we have a huge range of data, and then partition is just that I'm going to cut the data into small pieces, and then I will treat like each set of data differently. And then that's the whole point of partitioning. And partition has many different names. It's called like shard in MongoDB and lots of traditional database, or like in region in HBase, tablet in Bigtable, vNode in Cassandra, and all of them are some kind of a newer version of a distributed database. And later on, we will introduce some of the more practical real-world the database that industry is really using. And but like why do like this kind of practical system or like the everyday the database that you use every day need to have this concept of partitioning? What is it so special that we want to partition or break the data into smaller pieces? And the idea first, remember we should focus on the abstraction. The way you think about the data set or the way you think about the whole database is pretty simple. Here, you can think of it as a dictionary. So by dictionary, actually you can think about like, for example, maybe it's a hash map or something. So here you have some key space. So like remember, like before we mentioned that this is a simple abstraction of a key value pair. You can think about, you can actually treat the database as a that kind of data structure. So it's a dictionary. And then partition, just that suppose you partition the data set according to your key. So the first range of a key value pair is your partition 1, and then second range is your partition 2, so on and so forth. So that's the notion of abstraction. Okay. Then next, once we have this notion, why do we care? Because the idea is about scalability. So how does this notion of partitioning help in terms of scalability? And then that's because that if you remember the data set, how do we use them? Like this kind of distributed storage, that the key thing about this distributed storage is that if you want to access some data or if you want to access multiple data together, you need to have some coordination, and coordination is expensive. So the key for partitioning is that suppose I have sorry, here. Suppose I have 3 nodes or 3 servers, and then I can assign one partition to one server. So by this arrow, it means that the server 1, or let's call it server A, and will handle only this data set in like P1, partition 1, and server B will only handle the data inside P2, C only handles the data inside P3. So let's suppose I'm a client, then if I am only interested in data in P1, then I only need to contact server A. I don't need to ask like what B or C has. And then this reduce the amount of coordination you need. So it's much faster. And then in terms of the kind of a more formal way of saying is that we avoid coordination. So in hope that the throughput should be linear in the number of servers. So if you read lots of kind of performance evaluation or benchmarking, you will want to see some kind of a figure, something like this, where x-axis is that the number of servers or like the number of clients, and then the y-axis is like the throughput. So usually throughput is like operation per second. Then you will want to see a linear kind of increase in throughput if you add more servers or you add client. And then this can only be achieved if you do partitioning. Because that if that you don't do partitioning, so suppose in this case, A needs to store everything, B needs to store everything, C needs to store everything. Then when you access something, basically you need to contact everyone. Then actually your throughput will not increase. Okay. So that's the whole idea of partitioning. And why do we want that? Then in practice, actually like people just don't use a partition by itself because we still need to deal with failure, or if like some of the server is too slow, then we need to make sure that the slow node doesn't really affect the performance. So we also do replication at the same time. So the idea is that so we have like, oh, let me draw it. We have like server A, server B, server C, and then server A will actually handle P1 and P2, two partition, and then server B will handle P2, P3, and then server C will handle like P3 and P1. Okay, so that's how you do the replication and partition at the same time. So that your whole database or whole dictionary will be partitioned into multiple shards, or that you have multiple partitions, and then a single node, a physical node or virtual node, they may store multiple partitions. And then that's usually how that practical system kind of replicate and store the data set. Okay. Then the next thing is that, okay, now we know that partition is really good. It helps with performance. I also know that you need to do some replication. But then fundamental questions in this area is that what is the best way to partition? What is the best way to assign different partition to different set of nodes? And some of the tricky issue here is that you need to handle the dynamic workload. So by workload is that as a client, I will access some of the key value pair. Then you might access the other set of key value pair at different times. And then this workload may change over time. So how do I handle that? And then oftentimes that the workload is actually skewed. So what do I mean by skewed is that there will be some data item that's really hot, and some of the data item that's not as popular. And that really makes a lot of sense, especially in that kind of social network application. For example, Facebook or Instagram, then some of the kind of stars or like key influencer, their post or their image, their photo will be super hot. Everyone wants to access those. But like if like for example I post something, then you might not want to see it. So that this skill workload is like very difficult to handle. So why is that? The idea is that suppose like somehow again we have like server ABC, and somehow, like if you partition the data into a very EO form, suppose that all the superstars, like kind of Instagram photo is handled only by server A, and then B and C like kind of say handle like the post from academia people or like something else. Then that server A will soon will be blow up like very fast because everyone want to access it. So how do I make sure that the workload is kind of evenly distributed to three of the nodes or like all the server inside the system? Then that's a challenge that we need to address. And of course, once you throw in the distributed system thing, you have failures, and then you have asynchrony, your node may be slow, and all those things that you need to consider when you decide how to partition your data set. Okay. Then Strawman-solution is that since I don't know anything, I can just do random partition. So by that is maybe key A, I will randomly pick one of the nodes, say handles B, server B should handle it, and then key B, server C should handle it, so on and so forth. But here, think about it, this might work, and then this might work reasonably well, even with the skill workload. But what would be the difficulty when you want to implement this solution? The idea is that a priori, you don't really know who has which set of data. So suppose you have a new client comes in, and then say, okay, here, client. Then suppose this client said that, hey, I want to see LeBron James' Instagram post. But then the first thing is that it doesn't know which server to contact, right? So because it's random partition, maybe server A has it, or maybe server B has it, or maybe server C has. So the first step is that client need to go ask every server, say that, do you have this data? Do you have this data? Then now you already add more latency. And then that's usually not good. And even though some of the solution AS actually they have some kind of a directory service, basically track that who has which set of data, but like in general, we try to avoid this kind of dictionary or the directory kind of base design. And now, yeah. And the other way that in the book is that, okay, I can basically just do modular thing. So for example, here I have a 3 server. And then what do I mean by modular is that suppose I have some file name, say LBJ. Suppose that's his key, LeBron James key. Then you do mod, say mod3, because I have 3 server, and then that will tell you that, okay, which server has the LeBron James Instagram post. So that's good. That solves the problem of like tracking. But then the thing is that this doesn't really solve the skew workload or dynamic workload, right? Because that this thing is always fixed. And then the other kind of downside is that suppose I'm going to add more server into the system, then suddenly I need to reshuffle lots of partition or lots of data, because once I add more thing, this doesn't become 3, this becomes 4, then basically all the data that you need to reshuffle again, and which is very expensive. So we don't want to do that. And then one of the key things that we can do is that the idea of encyclopedia. And the thing is that similar to what I addressed before, or what I drew before, is that now I partition the data into many partitions, say 3 or even 100. Then what I do is that I don't directly doing mod on the data name. Instead, I doing mod that on the partition kind of a number. And then this is very suitable for data that rarely mutate. And then the other thing is that usually is if when we access the data, we try to access the data kind of continuously. So for example, I use LeBron James example again. Maybe I go to his Instagram and then I look at like multiple posts at the same time. So like usually that those data, those image will be in the same partition. Then you only need to contact with the same server again and again. And then in practice, that's usually much faster. If like, okay, I need to contact you, then I need to contact like server B later, then I need to contact server C later. This kind of moving pattern, yeah, is usually trickier to deal with. Okay. And then the other key concept in this area is that first I need to pick a good hash function. And then what I want to do is that I'm partitioned by hash of the key. So if you remember when we have this Strawman idea is that we want to do some random design. And then the idea of hash function is that suppose the data is the LBJ again, then I do a hash function. And then what hash function will give you, suppose you use a 32-bit function, it will map this data, the data name LBJ, or the key, then it will map into some integer, 0 to 2 to the power of 32 minus 1. Then what's the good thing about this hash function is if it's well designed, it means that the output, suppose that the output is 3, then this 3 thing will be, the output will be like uniformly rendered into this like data output space. So that's a very good thing. because that handle the skew workload pretty good. And then in practice, for example, MongoDB use MD5, Cassandra use Murmur3, and then lots of different systems use a different hash function. And I would say that it's still ongoing research to identify the best hash function to use in different scenarios. Okay. But the problem is that because if you treat each data name or the data key differently, then remember last time we said that we might want to do range query. I want to see the branches post consecutively. Then doing this hash of key thing is not very helpful because it's possible that the post is a hash to different servers. So in practical solution is that I can have compound primary key. So for each key, for each key value pair, you actually have two keys. One is a primary key, then the other is secondary key, so that you only hash the primary key. But for all the secondary keys, they will be in the same partition, and then they will be handled by the same server. Okay. And then the other practical concern is that we want to rebalance in the partition. So the first thing is that workload changes. Some of the posts that is not popular anymore, then you need to address that. And then when you might have a node failure, or that you have some server that's getting old, or some of the memory dies that has a degrading performance, you want to replace nodes, or you want to add servers. And here we need to reshuffle in the partition to different set of server so that the workload is kind of rebalanced. And some of the key goals are first, the new load should be evenly distributed to a new set of servers. And then ideally, you don't want to shut down the system and then do rebalancing and then provide the operation again, because most of the modern applications, we want to have this always on feature. Then I request always coming, and then I can continually serve you. And then the other one is more on the practical side, is that your network and net IO load actually is huge if your data set is huge. So suppose I had the Facebook data set, I don't know how large it is, but it must be a huge amount. And then if you need to reshuffle even small part of it, say 1% of it, it's already huge bandwidth consumption, and then your network actually will blow up. So how to do this without a very small overhead? And then I believe that's also an open area for research. Okay. And then the key exercise I want you to think about is that suppose the idea we have again, so that we do a hash value and then we do a modular n, where n is the number of servers. Then actually this thing is not very efficient. So try to think about that. What's wrong with this? Okay, so that's all I want to share today. First, we understand the idea for partition, and we know why do we need it, and some of the key idea, how do we do partitioning. And then one very key challenge in partitioning is that suppose your workload change, suppose your server sets change, then you need to rebalancing, reshuffling. What is the best way to do that? And yep, that's all. Thank you.